Good morning. This is Dr. Doobie. You've learned how to analyze distillation columns with two chemicals, but what if there's more than two? After all, most situations involve multiple chemicals. Let's learn how to do that. Here is our example problem for multiple chemical distillations. 100 moles per second of a saturated liquid is fed to the fourth tray of a 7-tray distillation column equipped with a total condenser and a partial reboiler. The feed consists of 30 mole percent benzene, 40 mole percent chlorobenzene, and 30 mole percent 1,3-dichlorobenzene. The distillate flow rate is 50 moles per second, and the reflux ratio is 0.5. Calculate all flow rates, compositions, and temperatures. Assume equal molal overflow and equilibrium stages. You can watch the tutorial on the Lewis method to find the development of all the equations that define this distillation column. Let's just look quickly, though, at the degree of freedom analysis at the top of the column. We have the vapor from stage 1 coming into the total condenser, and we have a liquid, L0 plus D, leaving the condenser. This is at the bubble point of the mixture, and that will help us determine the temperature of the total condenser. The distillate here has composition XDB. I give it this extra subscript because we have the three chemicals. That's benzene, and C is for chlorobenzene. I don't write out the composition of the dichlorobenzene because, again, these all sum up to 1. Also, I don't write out the compositions of V1 and L0 because, as we know, they have the same composition as the distillate. So as we look at our degree of freedom analysis, we have our unknowns, and we'll have a certain number of those. We have V1, L0, TC, XDB, and XDC. So we have 1, 2, 3, 4, 5 unknowns. Now we look at our equations that we have available. Hopefully there's 5 of them. We have a total mole balance, and you remember that we don't have component mole balances because they're not independent, because they all have the same composition, all the streams. We have the bubble point equation, which is the equation that relates this composition here to the total condenser's temperature. We also have a process spec, which is the reflux ratio. This relates the value of L0 to D. So that's only 3 equations, and so we have 2 degrees of freedom. You might remember that with 2 chemicals, we had 1 degree of freedom, and we needed to make a guess. And so we will make a guess for the benzene composition in the distillate, but also we'll make a guess for the chlorobenzene composition. So we have 2 things to guess, and we'll check at the end of our calculation at the bottom of the column whether those compositions are the same as you would get from an overall mole balance. For phase equilibrium relationships, we'll assume Raoult's law because These chemicals are similar enough that they're probably an ideal solution. And remember that what we have is y is equal to kx, where K is the vapor pressure divided by the total pressure. And the vapor pressure is found from Antoine's equation, and it looks like this: 10 to the A minus B over T plus C. And those three constants are shown here on this table: A, B, and C for benzene, chlorobenzene, and dichlorobenzene. And note that the temperature in this equation is for degrees in Kelvin and the pressure in bar. Now, where did these come from? They're not in the back of Felder-Rousseau. So we'll do a Google search for the Antoine's constants for 1,3-dichlorobenzene. And you see the very first entry is from the NIST webbook. NIST is the National Institute of Standards and Technology, and they have lots of data. We'll click on that, and there's the chemical with all sorts of information. And we'll scroll down here to, let's see, the Antoine equation parameters. Sometimes you can get it there, sometimes from phase change data. If we go to phase change data, you see other things that are here, including heat of vaporization. But there's the Antoine's equation parameters. Now, the parameters come from this article, the data in this article, and it says here the coefficients were calculated by NIST from that data. And here are the coefficients. And it's in the temperature range 363 degrees K to 446 K. Now notice here's the Antoine's equation, and it's log 10 of the vapor pressure, but the vapor pressure is in bar and the temperature is in K, unlike the Antoine's constants, say, in the back of Felder and Rousseau, which are in millimeters of mercury and degrees C. So you just have to pay attention. So anyway, we can take this data and use this for our calculation of vapor pressure. Here is my spreadsheet solution. I won't describe it in great detail, but you can look at the tutorial on Lewis method for a detailed description of how the equations in the spreadsheet are developed. The distillate flow rate is 50, the reflux ratio is 0.5, and we had to make guesses for the benzene concentration and the chlorobenzene concentration in the distillate, and so I guessed 0.7 and 0.2. The stages are the total condenser, stage 1, the first tray is stage 2, second tray, third tray, fourth tray, etc., down to 9, which is the partial reboiler. So it's a 7-tray column with a total condenser and a partial reboiler. The feed goes into the 5th stage, or the 4th tray, and it's 100 moles per second. And here's the composition that was given in the problem statement. I cut off the feed columns just to make the other numbers here a little bigger for you. The liquid here, stage 1, is the reflux, and it is just the distillate flow rate times the reflux ratio. The vapor flow rate here, coming out of stage tray 1 into the total condenser, is the liquid reflux plus the distillate, so it's 75. The rest of the vapor flow rates are for the EMO assumption, and the liquid flow rates are all based on total mole balances. The vapor phase composition, leaving tray 1, it has to be the same as the distillate. But after that, they're all calculated based on a component mole balance. then the liquid composition is based on equilibrium with the vapor phase composition. So for instance, XB, the liquid composition leaving tray 1, is YB divided by K. The temperatures are chosen so that the bubble point equation or the dew point equation is equal to 0 because I put all the terms on one side of the equation. So Solver takes the initial guesses and calculates the temperature on down the column. And you see here I've already done that. It's the temperatures have all been correct based on our initial guesses. Now, here the composition in the bottoms is calculated using an overall mole balance and compared to the stage-by-stage calculation of the compositions of the bottoms. And then they're compared. They should equal 0 if we've chosen a correct guess for the distillate composition, but obviously they're not. This number is just too big for that cell. So now what we're going to do is ask Solver to go ahead and change these distillate compositions, run through the entire calculation of bubble points and dew points, compare the values here, and then continue that process until we have correct distillate compositions. So now Solver has done that. We have a benzene composition in the distillate of about 0.6 and a chlorobenzene composition of about 0.39. So quite different than my guess, which was 0.7 and 0.2. We only have 1% dichlorobenzene in the distillate, and we only have 0.1% benzene in the bottoms. But the benzene and chlorobenzene are substantial in the distillate, and the chlorobenzene and dichlorobenzene are substantial in the bottoms. Generally, it will take 3 columns to completely separate these 3 materials. This first column puts the benzene and chlorobenzene in one stream and the chlorobenzene and dichlorobenzene in another stream. Then a second column can separate these, and a third column can separate these. It's instructive to look at a presumably more accurate solution done by ChemCAD and compare that to our simplified method. And in this chart, we have the liquid flow rate and the plotted versus the stage. Now notice the ChemCAD solution is in blue and the flow rate is not constant in a given section of the column. For instance, at the top of the column, it goes down a little bit. At the bottom of the column, it's increased a lot because of the feed, but then it continues to increase. Whereas the Lewis method that we used, these flow rates are constant across the bottom or the top of the column because of the EMO assumption. We assume that liquid flow rate does not change. Here is the vapor flow rate plotted versus stage. And again, note that the Lewis method shows a constant vapor flow rate all the way through the column because of our EMO assumption. In the ChemCAD method, more rigorous method, it does change a little bit. ChemCAD does not use the EMO assumption, and they probably use a more accurate vapor-liquid equilibrium relationship than Raoult's law. Here is the liquid phase composition plotted versus stage, and the 3 chemicals are shown here. This is the benzene, and it has the highest concentration at the total condenser and goes down fairly steadily with a little kink here at the feed tray and is almost completely gone by the time we get to the total the partial reboiler. The heaviest component, dichlorobenzene, is almost non-existent at the distillate, but rises steadily through the column with a little kink here at the feed tray and is highest at the bottoms. The middle component has a stranger behavior. See, it's got this M shape. And this is really curious when you first see this. And in the book, I give a fairly detailed description of why it has this particular shape. Overall, I'm pleasantly surprised that our simplified Lewis method has produced such similar results to the more rigorous ChemCAD program. Here is the vapor phase composition versus stage, and again, we see that the compositions from the Lewis method are very, very similar to the more rigorous method used by ChemCAD. And finally, here we have the temperature plotted versus stage. And we see a very continuous increase in temperature as we go down the column. And the Lewis method has produced very similar temperatures as ChemCAD. You know that you have fed to probably the optimum stage when it's a fairly smooth transition in the temperature at the feed stage. There's not a big kink here. So that probably was the correct choice. It's a little harder to tell when you have three components. That's all I want to say about multi-component distillation. Give it a try with the chapter problems. The basic difference between this and the two-component distillation was we had to make an extra guess of distillate compositions.